Okay, so today we are going to discuss the last topic of non-linear data structure, that is shortest path algorithms. Now, actually, there are number of versions for these algorithms, but we are not going to discuss each one of them. Just for simplicity, we'll keep it a simple shortest path algorithm. Let us first understand what it means. For any given graph, let us say this one is a graph, right? It's a directed graph, and it's a weighted graph. You can see, because the direction is involved, and also there is a weight function associated with every edge. So for any given weighted directed graph, shortest path means that a group of group of edges from one vertex to another vertex, such that the total weight of all the edges is minimum. So that is our objective function. So for example, if I want to compute the shortest path from S to U, then you have to first identify what are the different path from S to U. So this is one path, right? Directly from S to U. There should be another as well. For example, S to X and X to U, right? So there are two paths available for S to U. One is S to U and second is SXU. So it means that shortest path means that total weight of all the edges which is making your path, or which is part of a path, should be minimum. So for example, if I consider this from S to U, the total weight is 10. But when it comes to second path from SXU, then total weight is 5 plus X to U is 3. So 5 plus 3 is 8. So that means the shortest path from S to U is SXU, right? So shortest path doesn't mean that you want to minimize the number of edges. Our objective is to minimize total weight of the complete path which connects two vertices. There are different versions of it, but single source shortest path, single destination shortest path, and there are many. But we are going to discuss the fundamental version, that is the single source shortest path. What it means, you have been given a source vertex. So here, this is your source vertex, right? S is my source vertex, and I want to compute the shortest path from S to U, S to X, S to V, and S to Y. So how to do that? This algorithm is basically very similar to the Prim's approach, right? The approach which we have used in the Prim's algorithm is quite similar. Actually, the Prim's approach was derived from this approach only, right? So let us first understand what we are supposed to do. So this is my initialization. So in the first iteration, what I will be doing is that I will make sure that the shortest path for source to source is 0, right? Obviously, the shortest path from S to S is 0, and initially shortest path from S to every other vertex is infinity, right? So this is my initial setup. So let us mention the path itself here, the total weight itself. So this is infinity, this is also infinity, and this is also infinity. What this actually indicates, it indicates that S is not currently connected to any of these vertex, and that's why the total weight is infinity. That means there is no way to reach at U via S. This is the initial setup. Now again you will use a priority queue, right? So similar to what we have used in this Prim's approach, we are using a priority queue, which is mean priority queue. So let's make one table for queue. Okay, we so this is my parent table which I require to maintain. Another one I told you that we'll maintain one queue. So let's write in a simple term that, because I don't want to write anything else. So initially, what you will do, you will insert the vertices in a queue. Every vertex will be inserted inside a queue. So S, U, X, V, and Y. All of them are inside a queue. Okay, so this is my initial setup, that your source vertex distance is 0. Every other vertex distance is infinity. You will maintain one parent table and you will maintain one queue. So this is my initialization. Now what am I supposed to do is that I want to extract a vertex from a queue. So when I extract a vertex from a queue, obviously it's a mean priority queue. So it means that the vertex with minimum key value will be extracted. Sorry for disturbance. So vertex with a minimum key value will be extracted. That means if you see the key value, this is 0, this is infinity, 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 and infinity. That means S will be extracted, right? So this will be extracted from a queue. Now check all the adjacent vertex of S. So there are two U and X, and update its distance. Now how you are going to update? You will check the distance of U. If it is less than the weight of SU, then this will be updated. So here distance of U is infinity and the weight of SU is 10. So that means this will be changed to 10. And at the same time, because you have connected U via S, then parent of U will be S, right? Second adjacent vertex of S is X. The current weight of, distance of X is infinity, and total, the weight between the vertex of S to X is 5. So 5 is less than infinity. That means this will be changed to 5, right? And at the same time, we will also update the parent of X. So parent of X is also S, right? So this is after first step. This was your initial queue. Now your queue will be changed to something like this because S is extracted, right? Next, again you will extract minimum from a queue. Okay, so what is the minimum? U, X, V, Y. There are four vertices in a queue: U, X, V, and Y. V and Y. So this is 10, this is 5, this is infinity, infinity. That means 5 is the minimum. So next, vertex. The Remember, this is not part of Q now. So let's change it something like this. And what is extracted? X is extracted. So now my Q will have only three vertex U, V and Y. So X is extracted. Again you will check all the adjacent vertex of X. So this is what extracted. Now check what are the adjacent vertex of X. So there is one edge which is going this, right? So U is an adjacent vertex. Second one is this. So V is adjacent. Third one is this. So infinity. So these are the three vertex which are adjacents U, V and Y for X. So now let us update the distance of all of this. So now what is the current weight of U? It's 10. What is the distance of X is 5. What is the weight of Ux is 3. 5 plus 3 is 8. 8 is less than 10. That means this will be changed to 8. And because now you are connecting U via X, so this parent table will be updated for U. And now parent of U will be X. Right. Next, another vertex V, it's infinity. What is the weight of X? It's 5. 5 plus 9, 14. 14 is less than infinity. So that means this will be changed to 14 and parent of V will be X. So parent of V will be X. Okay. Next is this 5. 5 plus 2 is 7. This is infinity. 7 is less than infinity. So that means this will be changed to 7 and parent of Y will be changed to X. So parent of Y is changed to X. Right? So this is after step 2. Again you will extract one more vertex from a Q. So right, S is already been removed from a Q, so you will now you again observe the Q. What are the vertices in a Q? U, V and Y. U is 8, V is 7 and Y is V is 14 and Y is 7. So that means Y will be extracted from a Q. Okay. Because Y is extracted, let's change its color. Right. So this is the vertex which we are required to process now. Find out what are the adjacent vertex. First, outgoing edges is this. So there is one adjacent vertex, that is V, and second outgoing edges is this, right? This is also outgoing edge which is going towards S. So there are two adjacent vertex. But now we'll understand that there is another condition which is required to update the weight, and that condition is that another vertex should be part of Q. So that means because S is not a part of Q, this will not be updated. So what is the required to be updated? It is this. So let us first calculate the distance. So this is 7. 7 plus 6 is 13. This is 14. 13 is less than 14. So this will be changed to 13. And at the same time, parent of V will be changed to Y. So parent of V is updated to Y. Right. So that's it. There are only two adjacent vertex of Y. So this is done. Next, you will extract one more vertex from a Q. Okay. So now you have two vertices in a Q, U and V, right? So which one is minimum? Minimum is U. So that means U will be expected. So only V will remain inside the Q. So this is processed. Okay. U is expected. So let's change its color. Okay, fine. Now, which are the adjacent vertex of U? There is one, right? Outgoing edge U to V. Another outgoing edge, this one, right? So there are only two outgoing edges from a U. So first let us take this. Okay, this is 8. 8 plus 1 is 9 and this is 13. So that means this will be changed to 9 and parent of V will be now updated to U. So this is U. Okay. Next is this vertex. So this is 8, 2, but the another vertex is not a part of Q, so you will ignore it. So this will be the status after this iteration. Then you have one more vertex in a queue. Remember, you are going to repeat this till your queue is empty. So now there is only one vertex inside a queue. That means my queue does not contain anything now. So queue is empty. This is processed. Okay. And V is expected. Right. Now again, obviously, there is no one in a queue. That means all the other vertices are out of queue. That means you will not require to change anything after in the last iteration. So at the end, what you have is this situation. So this is my output actually, right? So this is the output. So you have a distance of all the vertex from a source vertex, which will be minimum. And how can you compute path? For path, you require this matrix, right? So how? So if I change this table, I add one more column. Okay. So let us try to make it. So you have source vertex S, then the distance for U is 8, this is 9, 7 and 5. So distance is there, but now you are interested in computing the path. So how can you generate a path? Obviously you will go in the reverse. So for S, it's a source vertex, so there will not be any path, right? Then find out what is the parent of this vertex. So what is the parent of X is S. That means path from S to X directly, right? Again here, Y is child of X, or you can say Y is connected to the source vertex via X. So there is one path from Y to X. But remember, we are interested in path from a source vertex to every other vertex. So then again you have to append this path. What is the path of X is, sorry, I think this should be written like this for simplicity, right? So what is the path of X? Path of X is through S directly. So what you can have is this. Okay. Again, parent of U is X. So it means U is connected via X and X is directly connected to source. Okay. What about V? V is connected via U. Okay. Then you have to see this path for U. Whatever is there, you have to append it. So U is connected via X and that is directly connected to the source vertex. Right? So now you have a path from all other vertices to the source vertex. S to X directly. This is the shortest path, 0 to 5. Then for Y, you have S, X, Y. So S, X and Y. So 5 plus 2, 7. For U, you have U, X or S, X, U. So S, X, U. So you have 5 plus 3, 8. And for V, it is S, X, U, V. So S, X, U and V. So 5 plus 3, 8 plus 1, 9. Right? So by this way you can compute the shortest path, single source shortest path for any given graph, and this approach is actually known as Dijkstra's approach for shortest path. So let us quickly discuss the algorithm. Okay. So if you remember that we have a graph with weight function and one source vertex. So this S is a source vertex. In our case, in this example, S was a source vertex. Graph was given and weight function is given. Weight function means it represents the weight of all the edges. Okay. Initially, what we are doing, if you remember the initial setup, what we have done, the distance of S is 0, distance for every other vertex is infinity, parent of every other vertex is nil. So this was our initial setup. So what we have done, for each vertex V belongs to V of G, distance of V is infinity, and what you are doing, inserting that vertex inside a Q, right? Here there should be one change. It should be V of G minus S. Minus S means that you are not considering source vertex. Okay, you are not changing its key to infinity, right? You have already changed it to 0. So distance of source is 0 and you insert that inside a Q. Again you insert all other vertex inside a Q. Now what you can do, you can uh, okay, here in this case we have not inserted source vertex inside a Q, so you have adjusted its adjacent vertex separately, right? So because we are not inserting inside the queue, you have to write this loop. But for simplicity, what you can do, you can simply write distance of S is equal to 0, insert Q, or sorry, insert S inside a Q, and here you can change this for loop V of G minus S. Then you can skip this line because this while loop will take care of everything. So what we are doing in the while loop, while Q is not empty, you extract one vertex from a Q, right? Extract minimum vertex. So here S will be extracted first. Then for every adjacent vertex of S, see this, for every adjacent vertex of this V, if you are checking its another endpoint, if X belongs to V minus S, V is your set of vertex, S is the vertex which is being extracted from a Q, राइट? तो જ્યારે પણ जब भी कोई भी वर्टेक्स एक्सट्रैक्ट होगी तो उसका आप अलग से लिस्ट मेंटेन कर रहे हैं. दिस इज अ सेट, सिंपल सेट. तो इफ a new vertex which is been extracted is sorry, the adjacent vertex of this vertex, if it is not part of Q, sorry, if it is a part of Q, then you check its distance. Distance of X is greater than distance of V plus weight of Vx. If that is true, then you update the distance, update queue, and update parent. Okay. So there are lots of mistake in this algorithm, right? So you can ignore this. But I think you should understand the approach. No one is going to ask you the algorithm, right? You will be asked to, because you have a separate subject for that algorithms. In data structure, you may be asked to solve this, right? So you will be given some kind of a graph, and you have to find out the shortest distance using this algorithm. So I hope you have understood the approach. No need to worry about the algorithm. Like algorithm, you can write your own, but understand the approach first, and I hope that is clear. Any doubt? What we have done, initialization, then insert everything inside a queue, then extract one vertex, update the distance of its adjacent vertex if that adjacent vertex is not a part of, if it is a part of queue. If it is not a part of queue, then ignore it. This you will repeat till your queue is empty. So this is how you compute the shortest path for any given vertices. Sorry, any given graph. Any doubt in this? Yes, anyone has anything which required to be cleared? Okay. So I think with this I will end the session today, right? So we have completed our syllabus actually, but you give your midsem exam first, prepare for midsem exam first, and then we may discuss something which is or it's kind of a revision in the next week, or if you require something which is to be discussed, you can ask me, you can mail me personally as well, that something which you want to discuss with me which you have not understood properly, so that we can discuss one on one as well, right? So that's it from my side for today. Still I am saying that if you have any doubt regarding any topic from a data structure, you can talk to me, you can write to me, you can discuss on classroom as well, or you can mail me as well for the same. Okay, so that's it for today.